great pleasure to introduce this Professor Umesh Kadhane. So I know him from my graduate when I was in TIFR. He joined 1 year after me, and so he finished his PhD from Tata Institute of Fundamental Research, and then he had experiences, and he was working on the ion molecule collisions in TIFR, and then he moved to a few places as a postdoc. And so he was working in the molecular mass spectrometry at the University of Aarhus, Denmark. And then he moved to, I think, Paris, University of Paris, Sud, which is at Orsay, France. Then he started his academic career in India, so in the Department of Physics, which is IIT Madras, since 2008, December. Then he was there for 2 years. After that, he moved to the newly formed Indian Institute of Space Science and Technology, where he started his career. And he is now is a full professor there. And also he is the head of the department in the physics department. And he has contributed many research activities in that space science research, and mostly the plasma propulsion systems, which is developed by LPSC and ISRO. And he has many many students graduated from him. I think around 6 already graduated. And now he's working on these setups, and he developed 3 major research laboratories at IIST, and which is actually looking for the fundamental atomic and molecular physics research, and also for the 2 space-oriented research and development. So with this, I request Umesh to take over, and then we are looking for his nice talk. Thank you.
Thank you. Thanks, Dhananjay. It's very nice to see you all after a long time. Due to this COVID situation, we are not able to meet that often. So thank you very much for this very nice opportunity and very nice interaction opportunity for me. And I would like to talk about something which is more like a dream. So I expect that by the end you will understand what is written in the last 2 lines. Hazaro khwahishein aisi ke har khwahish pe dam nikle. So I will come back to it at the end. So basically the idea is to search for the molecular seed of life in our solar system. Why I say it's a mission plan will be visible in the last 3 slides. So before we start on the topic, I would like to, just a minute somehow. Slide down, okay. So our institute is not very old, but not very new. Not very new and not very old. It started in 2007. It's in the southern tip of India, in the city of Thiruvananthapuram. And just a minute, I'll just get a good laser pointer. I believe my pointer is visible. So at this point is Thiruvananthapuram city, and we are slightly on the outskirts of the city. This is our campus. I'll not describe it. It is India's and Asia's first space university, and we are obviously directly related to Department of Space. In the institute, we work in atomic and molecular physics lab, and we have a very large swath of activities: molecular physics, electric propulsion research. We build space-borne sensors, as well as we are supporting a cold atom-based research activity for ISRO. But now after spending almost 11 years in this struggle, it is now time to take molecular physics to space. So I will talk a little bit about that after just going through a few photographs. So this is our electric propulsion laboratory we have set up at IIST. This is a complementary lab to what is already there in Indian Space Research Organization. So this is actually funded by ISRO. We worked with this kind of electric thrusters, and we help ISRO do their diagnostics and testing and so on. And we built the hardware. So this hardware, what you see here is the diagnostic package, which we have built for ISRO, and that is supplied. So we supply it to ISRO. It is used for testing the electric thrusters. It's basically oriented towards plasma and beam optics and beam diagnostics. Then, as I said, we built small payloads also. So this was our first payload, which was launched in 2019. It's called ARIS. It was a retarding potential analyzer to study plasma environment around Earth. We are getting ready with another payload, which is called IDM. I am not getting into the details, which will go on to the technology demonstration satellite next year to be launched. We have a payload slotted for the next Mars mission, next Venus mission, and a few more ideas are being floated right now. So let me come back to the molecular physics. Basically, I'm sure many of us are intrigued by this. Some of us are actually working in this field. So it all started with pHs. It's a theory of the pH universe, where we expected that a large quantity of pHs, polycyclic aromatic hydrocarbons, are present in the interstellar medium. So these are just two examples, and these are very standard examples. You can have many more examples just to show how abundant they are. So I'll not get into this. If needed, we can get into the details of this. But in this figure, the ratio of molecular hydrogen to pH is compared, and you can actually see the abundance in a very large quantity. The green color is basically hydrogen, and the red one is coming from pHs. And then the ratio is plotted on this side, and you can see a large quantity of pHs being present. Now, what is so surprising about these molecules being present in the interstellar medium? Again, I'm sure many of you are already aware that these are organic molecules, generally not so strong like aluminum oxide or silicon dioxide or something. So it's really surprising that how do they survive in a very harsh environment in space? And when you detect them from Earth, for example, you are really seeing molecular population which has survived for millions and millions of years. So it's not just a transient phenomena, they just exist in very large quantities. And in fact, in 2010 around, even the explicit signatures of carbon-60 in interstellar medium was also reported. So these molecules are very common. Initially, it started out as explaining some unidentified infrared bands, and then it turned out that they are there everywhere in all galaxies, and all very, very large quantities they were found. So now people are trying to understand how they are formed and how they survive and so on. And this became a scientific investigation in itself with many branches. So we started our work with that. So typically what we were looking for is you take a pH molecule and you sort of shoot it with high energy electromagnetic radiation or charged particle radiation. So one is, of course, you can have a direct damage, but generally at higher energies, you don't really cause a direct damage to a molecule. The molecule, particularly molecules like pHs, they have a very interesting tendency to absorb this energy and digest it very quickly. And when I say very quickly, it literally means in picoseconds. It can digest it amongst many vibrational modes of this molecule. And then it uses this energy to basically damage itself deliberately. It's like very, very metaphorically speaking, damage itself, so that the energy is used for something. So these pHs, for example, this is one example where you can see these white dots are basically hydrogen atoms. So they are used as a loose change, and this energy is used in eliminating them. In the process, you consume this excess energy, and you also produce a structure which is chemically quite active. And then these structures can also undergo some photoexcitation or energetic interactions, and then they can undergo something called isomerization, and then they can form more complex structures. So the prevailing understanding of this progression is like this, that you start with small pHs, you can isomerize and start larger structures. you can break and form different kind of structures. So different mechanisms like dehydrogenation and fragmentation will give you smaller pieces, and isomerization can give you more complex pieces. So this is a prevailing understanding, and there is a lot of interesting science in it, how these molecules do this, how they change their shapes, and how they lose hydrogen, how they rearrange hydrogen, and we have been working on this. So while studying this, often we come across a measurement which actually matches with this kind of graph. Okay, so what is this graph? So basically I have deposited some energy into my molecule, and that molecule is now digesting that energy, and it is spread thermodynamically or statistically, it is spread over all the vibrational modes of the molecule. And then you will have a certain damage process, which I talked about. So my internal energy is on the x-axis and the dissociation rate is on y-axis. And this is a very typical example of naphthalene. So the picture which I was showing here, this is the picture. So this is how its various decays were reported, like hydrogen loss and C2H2 loss. You can see the y-axis is in log scale. So these decay rates change very rapidly for even a small change in the internal energy. So when you're doing such experiments, if you want to measure such processes experimentally, it is very complicated. It's very complex. For the simple reason, you can imagine now, you need to know the internal energy very accurately so that you can actually measure the decay rate, because the decay rates are extremely sensitive to the internal energy. So this is very interesting domain where a lot of interesting experiments were attempted. I'll come back to it. So this is the premise on which we started our activity about 10 years back at IIST, and to explore these statistical processes. And this is just one example. We have also looked into quinoline, how it loses hydrogen cyanide and so on. And we were looking into that also. So we developed collaborations, we developed instrumentation to study these in different ways. So I think, yeah. So basically we use low energy protons using electron cyclotron ion source at IUSC New Delhi. We also go to synchrotron radiation sources where we do electron spectroscopy, photo-electron coincidence spectroscopy, and so on. We have built electron impact setup at IIST. We have also a very special type of energy analyzer combined with time of flight mass spectrometer, which I will be talking about again today. So we have developed different type of instruments. We have developed collaborations with people have that sort of capability to basically address these problems. So these are the two instruments which we built at IIST. This is an E2E experiment. Basically, this can do electron impact, secondary electron energy analysis, and then in coincidence, a mass analysis. So this instrument is built and it is in use regularly. Then this is the ion neutral coincidence spectrometer. We haven't really used its capability because we have recently developed a very unique technique, which I wish to spend some time upon today. And I will show you some nice results, but this instrument has even more potential to grow. These are the two facilities we use outside IIST. So one is a gas phase beamline at Trieste, and the other one is a LEIBF facility at IUSC. And so in the beginning, we started with the various mechanisms by which energy can be deposited into PAHs. It's a very large family, as you know. So we had to start with the smallest of the member of this family, that is naphthalene. So we started with naphthalene, azulene, then we went to quinoline, anthracene, and so on. So in naphthalene, you basically can have H loss, H2 loss, C2H2 loss, and so on. So we studied the effects of plasmon excitation and how this plasmon excitation heats the molecule sufficiently high temperature so that it can lose these fragments at a certain rate, and we could quantify that. Then we studied how the other modes of energy transfer by a continuous energy loss, electronic energy loss, and so on, how the charged particles deposit energy into the molecule. We further studied very interesting effect of how one PAH can undergo isomerization due to charged particle collision, and that was also very interesting phenomena. and so on. And then we studied multi-plasmon excitation also, but you can find the details in these references. But yeah, so far the picture was like I'm dealing with the molecule in isolation, and it's like in interstellar medium, the molecule is very much in isolation. So once in a while, it will, once in a day, once in a week, sometimes once in a year, it will receive a very high energy UV photon, and then it has to digest that energy, and it has a lot of amount of time to go through various decay processes. So when it comes to laboratory scale, unfortunately, when you have a molecular ion at hand, you don't have that much time. So time is very important for your measurements. You can't simply say, okay, let me wait for 2 days and see what happens to the molecule. And of course, there are other issues. Like for example, in polycyclic aromatic hydrocarbons, if you heat them, they would like to cool. If you heat them and you watch them over, say, a few milliseconds, and if they cannot break, if they cannot fragment, they will start losing energy by emission of IR radiation. So definitely the experiments which you would like to do should be at a time scale shorter than milliseconds. And at the same time, the experiment should give you enough fidelity so that you can actually make a rate energy diagram, that is the internal energy and the decay rate diagram, and you should be able to make a correlation. So we required an instrument which can cover a certain time and energy range. So the prevailing instrumentation, typical, these are typical ranges. There are specialized instruments which can cover these ranges. They are very specialized and built for special purposes. So this is one typical example where if you have a linear time of light, the molecules have to decay at the rate of something like 1 microsecond. The decay time scale should be like a microsecond or less, so that you can see its effects when you take a mass spectrum. If you have an ion storage ring, of course, you can extend this to milliseconds. You can go from several hundred microseconds to milliseconds. You can make the molecular ion survive and then look at those decays. But in case of PAHs and PANHs, at least, this time range is not very interesting, because then they will start emitting IR radiation and then they will start cooling down. And then I do not know what amount of internal energy is left in my molecule. So it becomes very complicated. So the most interesting time scale is basically between this sub-microsecond to something like close to millisecond. This time scale was vacant because the instrumentation requirements are a little tricky. So this is the region which we recently filled with a new instrument. So we built this instrument long back for ion neutral collision, coincidence measurement, but then in the whole process, Vinita was working, one of my PhD student, and then we started looking into the data in more details, and we could develop this technique. So the idea is very simple. We have three electrodes where we apply voltages to accelerate the ions. Positive voltage is applied to the first plate, and then gradually the voltage goes down. And then you just shoot a nanosecond laser, UV nanosecond laser, and the target molecule is effused in the center, and you ionize, and then these ions are extracted by this DC field towards an energy analyzer. So this energy analyzer is a large parallel plate analyzer. And then by applying the correct voltage on this plate, we can bend the beam of ions towards this position sensitive microchannel plate detector. Now, obviously the range of these ions is decided by their charge to energy to charge ratio, kinetic energy by charge ratio. And being a pure electrostatic configuration, it is not sensitive to mass. So all charged particles with the same E by Q ratio will come at the same point on the MCP detector. But suppose the molecular ion is totally accelerated, and in this drift region, that molecule breaks. If it breaks and releases a neutral fragment, then proportionately a certain amount of mass, proportionate to the mass, a certain kinetic energy is taken away. So the charged fragment now has a proportionately less kinetic energy. So it will not have the same range, it will have a shorter range. So this is the phenomena which we in principle use. An excited molecule in our case can break apart. If it breaks apart within, say, few hundred nanoseconds, it will have an effect of this electric field imprinted on it. If it breaks instantaneously or less than 100 nanoseconds, then it will come as a fragment ion. If it breaks within a few hundred nanoseconds, the electric field effects will come. If it breaks within 1 microsecond to 10 microsecond, it can break anywhere here. Then it will come at a different location. If it breaks inside the parallel plate, it will come at a different location on the time of flight as well as the position on the detector. So this is the feature which we actually analyze in more detail. So typically the mass spectra will simply look like this. And we took one example of another pH, this is called fluorine. And we can get a very good mass resolution, better than 3000, and a very high energy resolution also. So this is just a typical mass spectra which I'm showing here. And if I take this mass, okay, and look at, I just cut this spectrum, I take these points and look at their position on the microchannel plate, I see these two bands. Okay, this is at the higher range in energy, and this is at a shorter range. So what we understand is that this is the hydrogen loss fragment, which is formed almost instantaneously after photoexcitation, and therefore it comes with the full energy. And the other one is formed later after acceleration. So it broke on the path. So its kinetic energy was lost and it came at a lower range. But you can see the time of flight is same. So this is the feature which we then further analyze. So we plot now time. This is only position. This is time of flight and this is position. So we combine these two into a plot. This is called the time of flight versus kinetic energy plot. So you can see energy correlated diagram now. So this is on x-axis, I have the time of flight, and on the y-axis, I have the energy spectra. So that's why you can see the parent ion has a single energy. So that's why it comes as a single dot, but the have two different energies. So they come as two different spots. Okay. So fine, this diagram looks interesting, and the decay which happens inside this parallel plate analyzer, that decay gives rise to this kind of tail connecting the parent to the slow daughter ion. So now, okay, fine, this looks fine, but what more information can I get out of this? So considering the complication of this data, you can't simply extract the information out of this just by looking at it or by taking area under the curve. So we had to do some simulations. So we did we had a very nice Monte Carlo code which was written to take care of all the electric fields, geometry, and thermal spread, as well as the laser beam spread and everything. And then we simulate this using, and what we feed in is the decay rate of a particular process. So we identify the decay process, we feed in the decay rate, and my simulation gives me a pattern. So you can see this is the pattern I get with my simulation when I give two decay rates. One is 10 to the power 3 and another one is 10 to the power 6 per second. So this is like a microsecond decay, another one is a millisecond decay. So you can see the millisecond decay fellow gives me the parent ion. It doesn't break within the time scale of my experiment, but the microsecond decay gives me a feature which looks very much like what I see in my experiment. Then we can do a comparison. We actually plot their intensities together and then match the decay rates and extract the decay rate. So we are capable now of identifying whether, so for example, if your molecule loses two hydrogens, equivalent masses, it is very difficult in an ordinary instrument to figure out whether the two masses were lost together as a molecular hydrogen or they were lost separately as two atoms. Now for astronomers, this is a very important information because that could actually help identifying the sources of molecular hydrogen in interstellar medium. So it is very important to identify whether my two mass loss is basically a molecular hydrogen loss or an atomic hydrogen loss in sequence. Now, this instrument is very much capable of doing that. So one example is this. This is azulene. This is another PAH. And here we can show how two hydrogens, this is the parent azulene, and then it loses one hydrogen and it loses second hydrogen in sequence. If it loses two hydrogens together, which is like a molecular hydrogen, then you can see it actually comes here. So this is the place where you will see it, and we can actually identify exactly, and not just identify, we can even measure its decay rate, at what rate this was formed. That also can be extracted out of this data. So that way, this is a very unique capability which we have developed. But that is fine. Now you have found out at what rate the decay is happening, but you also need to know how much energy was there inside your molecule. I'm not getting into the details, but again here, another model, this was an existing model, we just adopted it for PAHs, And this model is a multi-photon absorption model which we use, and we have drastically simplified the experimental technique. Instead of using a pump probe technique, we can actually drastically do a simplified experiment can be done even with a simple nanosecond laser, and we can actually get the rate energy curve. So this is fine. This is very nice information. We started getting this information, and then we wanted to understand now where can I use this information. So in the process, we said, okay, we are dealing with polycyclic aromatic hydrocarbons. What about nitrogen containing hydrocarbons? So we started doing some experiments with synchrotron and so on, as well as charged particle collisions with PANHs. So PAHs are polycyclic aromatic hydrocarbons, and PANHs are polycyclic aromatic nitrogen containing hydrocarbons. So we started working with them also. And then in this process, we started discovering some interesting phenomena. We started detecting certain decay processes which were not reported before. One of them only I will quote here. We could see that if I put a very high energy proton, something like 100 keV proton, onto a molecule called quinoline. That quinoline is just like naphthalene, but one of the carbon is replaced with nitrogen. I can produce HCNH plus, and the significance of this will come very soon. So it is called HCNH plus. So hydrogen cyanide with a proton attached. So when we saw this, that was little surprising. That, I mean, this is not something which you normally see in experiments. For many interesting reasons, this particular species, it's a radical HCNH plus, is sorry, it's not a HCNH plus. HCNH plus is not a radical. HCNH plus has been seen in space, and not in space. I will show you where else it has been detected, and its source is still unclear. How do you produce this? Okay, so this started us thinking. Then we started getting into the literature. This was a totally parallel study. It was not related to our mainstream study, but it was interesting. Then we started looking in more detail into our quinoline data, and we started discovering more interesting effects. Last year, we did one more experiment at IIST with synchrotron radiation, and we started getting some additional information, which again, I will come to, which is related to this last line. We could see that these molecules have potential to produce prebiotic molecule, meaning these molecules can actually finally produce amino acids and nucleobases. But that is very strange because, well, the obvious question you will ask is, to be able to do this, first I have to have that PANH formed somehow in interstellar medium. So this was basically a sequence of thoughts. So we started with decay rates and energy, internal energy measurement. We built the instrument. We started doing experiments. We tried to connect our measurements with other measurements, and then we started understanding, oh, there's something strange happening. And some measurements at IUSC, some measurements at ILATRA. And then that got us thinking into getting into this HCN, HNC business. And then when we dug deeper, we discovered that this is not the only thing. It actually is producing many more species. Today, I don't have much time to explain to you, but maybe someday I'll give you the details. So now, then we started looking into the astronomy aspect of it, and we started discovering more and more information, which was sort of complementing what we are observing in the experiment. And well, to be honest, we are not the first ones to do such things. Many people have detected such effects in laboratory experiments, and they have also made their own conclusions. So we started looking into the literature. We started looking into what information we have about comets, what information we have about asteroids, meteorites, dwarf planets, moon, and the literature is really filled with clues and ideas and suggestions and theories and models. So I'll not list everything here, but I have selected a few cases out of all these to talk about. So the first one is this. This is a very famous picture. It's called the molecular zoo. These are you can see the list of molecules. These molecules were actually experimentally detected on the surface of a comet, that is 67P Churyumov-Gerasimenko. This was the Rosetta mission. It was it was an excellent mission. I mean, the orbiter worked very nicely and gave a huge amount of information. The lander, if you remember, very famous, the Philae lander couldn't really anchor onto the comet. If that it could do, it could give us much more information. What is interesting is even for that brief few hours where the mass spectrometer was working, it could detect very interesting molecular species there, including glycine. Okay, and I will come to this particular molecule again because it just detected glycine, but there is a catch. Okay, but it detected many other molecules, ordinary molecules, oxygen, nitrogen, hydrogen cyanide, which are very common, methane, and so on. But very uncommon molecules. Glycine is just one of them, but there are formic acid, acetic acid, and so on, and many interesting species which you normally don't see. For example, cyanogen and so on. You don't normally get them easily. So these molecules were present on a comet. So it's like a molecular zoo. And how this zoo was formed, and that is where I will come back to this line again, is that in the process of studying this high energy radiation collisions, instead of getting into the technical details of that, I'm just giving a hint that we see that this radiation does play a role in producing such molecules. And then in the space, we see that there are evidences that actually show such things do happen. This was not a sporadic example, by the way. This is just the second comet where we could actually do an in situ, not in situ, but a sample analysis of a comet. A previous mission, Stardust mission, where one of the Wild 2 comet, some samples were brought to Earth and they were analyzed, and there also a large number of organic molecules were detected. So then comes meteorites. There are several types of meteorites, and there is a class of meteorites which are carbonaceous. And in those meteorites, again, there are subclasses, Allende and Murchison, and they are also rich in these pHs. Now, remember, a meteorite, when it falls on Earth, the surface undergoes a huge amount of heating and lots of damage. But the interior of this meteorite is relatively protected, preserved. And this interior contains these molecules, and not in small quantity, in very large quantities. So it is very interesting that these fellows brought it to Earth. And if you look into the details of how a very qualitative model of how these meteorites were originally formed as asteroids in the formation of our solar system, it shows that that means it has been scooping material at that time and collecting it. And now that time capsule is brought to us, which contains these molecules. And these molecules, we know now that when they interact with high energy radiation, they produce molecules which can actually breed life. So now it should be very important for us, for humankind, to find out those material surfaces in our solar system which are getting exposed to radiation for billion years or more, because our Earth existed for almost 4.5 billion years. So that means they have been irradiated. So we do not know what sort of molecular khichdi is being cooked in our solar system alone, and we should look into it. So this is one example. The third example, this is a very not so very interesting dwarf planet. It sits between Jupiter and Mars. There is a big asteroid belt between these two. And this is the largest of the asteroids. So it is actually labeled as a dwarf planet. It is about 1,000 kilometers in diameter, Cirrus. Its name is Cirrus. So it looks like a piece of rock, just like an asteroid. Just looks very dry place, gray, and so on. Till the time that people started seeing pictures like this, very bright white spot here. And then people started this sort of investigating it, and this happened in 2015 around. And then in 2018, people discovered, using a space mission, Dawn mission, people could actually conclude that this full planet or dwarf planet, 40% of its surface is graphitized carbon, 40% of its surface. But that alone is not sufficient, because it could be simply, powder of graphite, who knows? It's a bone dry place. No, it's not bone dry place. The whole mini planet is covered with an ocean of liquid water. So below this surface, over the whole planet, there is an ocean, and in liquid state. but the surface temperatures are way below the freezing point. So how is it in liquid state? Because it is mixed with salts, inorganic salts. And these salts make sure that this water doesn't freeze to ice. It remains in liquid form. And whenever a small asteroid hits this fellow, the surface gets punctured for small size, a puncture is developed, and then the water with the salt comes out. And the moment it comes out, it freezes and forms these bright spots. Basically, these are salt mountains, which came out with the water. And of course, the water goes to the space because of the evaporation. So now comes the question. Does it mean that this, because you can see there are so many hit marks, so many meteorites and so many asteroids must have hit this surface, and so many times the water must have come to the surface. Would it cause any chemical reaction? Moreover, there is continuously high energy solar radiation, charged particles, all protons, electrons, and then high energy UV radiation, extreme UV radiation is bombarded onto this. So a lot of chemical reactions are definitely possible. One needs to go there. This picture came in 2018. So we are still, we don't really know much about this fellow. And now people are planning some missions towards it. And I will also come to the end of my talk. I will come to this fellow again. I am hoping that I am taking a little bit of time. Okay, so the second, the fourth example here is Pluto. So this is what we knew. This is what the best quality photograph we had of Pluto before New Horizons mission, which took this photograph on the left-hand side. And you can see the difference in the quality. Well, fine, you had a better camera, you took a better picture, simple. It's not that simple. Pluto is so far away in our solar system. Well, you call it planet, mini planet, or not a planet, whatever, but something, some object. It's so far away, you don't expect much of dynamics there. But this heart shape is basically nitrogen ice. So, okay, we will escape that. But this part, the brown red color, is basically a material called tholene. Okay, and this material is not exclusive to Pluto. These tholins are formed in many other places in our solar system, and not in small quantity. You can see Pluto, a huge surface of Pluto is simply covered with tholene. And what is tholene? Tholene is a name given by Carl Sagan and Khare and a group of people. And this tholene is basically a sort of a complex polymer formed by carbon, hydrogen, and nitrogen. Mostly carbon, hydrogen, and oxygen, carbon, nitrogen, and hydrogen, carbon, nitrogen, and hydrogen. And you can have other things also, but mainly carbon, nitrogen. And we still do not know what this material is. We just know that it is formed. If you take a quartz tube and you produce a discharge in a gas mixture of nitrogen and methane, you will produce this. But by small change in the conditions, you will produce very different type of tholene. So what tholene is produced there and what you can produce in the lab, they could be totally different. So this is another area of research. Slow amount of research is going on because the processes are so complex. It's very difficult to do a very systematic study. So people are just right now searching in the dark. So the best way to address this problem is to go there and actually check what that material is. That will guide us much better, because people tried from 1984, people tried to create this material in the lab. But yeah, I mean, every time people end up producing some material, it has some characteristics, but everybody seemed to produce a different material than the others. So we still have to understand what is there actually. Tholene is a large class of material. We need to understand it. Okay. Then finally, I come to the hero of the story, that is Titan. So this moon of Saturn is very peculiar. It is very large, more than 3,000 kilometers, and it has a dense atmosphere. The atmosphere at the sea level of Titan is 1.5 bar, and it is mostly methane and nitrogen. It's a very poisonous place, actually. It's filled with lots of aerosols and nitrogen containing cyanides and so on. So it's very dangerous place for humans, but it's a very biologically or pre-biologically very active place. And again, the whole surface, this is an actual photograph taken by Huygens probe, which landed. This is the furthest landing humans have done. And this is a beautiful photograph of the surface, is actual photograph. What you see in this are mostly ice rocks, mostly methane rocks. And this brownish powder which you see are basically tholins. Okay, so the whole atmosphere is filled with tholins and tholin particles, as well as aerosols and lots of hydrocarbons. And why this is a hero of the story is because we have actually gone there and measured the mass spectra, taken the data, and people understand the composition in much more detail than any other Jovian planet or Jovian moon. So that is anything above beyond Mars, where we know very little about their composition directly in situ. But for this, we know a lot because of one mission. Okay, so this is again a topic of a lot of discussion. But why Titan becomes very interesting to in my view, becomes important to our community here in atomic and molecular physics is because of this picture. So Titan by itself doesn't have very strong magnetic field, but the magnetic field of Saturn guides the charged particle radiation onto Titan. Okay, this is very well understood, very well known and measured. Okay, and because of this, interestingly, Titan has two ionospheres, one around 1,000 kilometers height and another one which is less than 100 kilometers or about 100 kilometers. Why? The inside one is actually created by the cosmic radiation, GeV energy, cosmic radiation, losing energy, going in and then producing a sort of a quasi plasma there. So it's a very dynamic system, and receiving bombardment of charged particle radiation in a very peculiar range. Again, it is important for Indian AMP community, I feel, because the energy ranges are in tens of kilo electron volts, and we have electrons, cyclotron ion sources in India, multiple of them, where such facilities can be done, such experimentation can be done, and we can understand. And also a few keV energy electrons also are guided onto this atmosphere. And the dynamism of this atmosphere, the chemical dynamism of this atmosphere is governed by this high energy radiation. So I'm running out of time, so I will just show you some pictures. So this is the actual data taken by INMS and CAPS payloads from the Cassini mission. And you can actually see the mass spectra up to, so in this spectrum, and the top left, you see the masses up to seven carbon atoms. But if you see the analysis in the higher mass side, actually it has prominent peaks in higher masses, also up to 300, and they are all separated by roughly 12 mass units. So definitely they are basically carbon compounds. So we have to understand their composition, their properties and so on. Are they the same ones which we could possibly have on Earth, or they are something special? We don't know today. So this is the composition of that, but again, in the want of time, I will avoid this. But you can see in the neutrals, they produce so many different types. This is the composition, the actual measured composition of Titan atmosphere, and you can see so many different molecules are produced. And there are ions, negative as well as positive ions in Titan atmosphere, which is again a topic of high research, high amount of research. And this fellow here is HCNH plus. Is what actually started us into this business. We are still discovering a lot of things in this going on. Now, very quick word, conventional ideas are like this. You start with nitrogen and methane and you put high energy radiation and you build. So basically the conventional approach is bottom up approach, meaning you start with small molecules, you ionize them, you damage them, then they do chemistry, and then you build larger structures. Yes, it is interesting, but you can imagine just to predict different fragments, people have to make models like what is shown on the left. Oh, sorry, the reference is missing. I have that reference somewhere. It was there, but I think somewhere it got lost. So you can see what sort of crazy models people have to make. And then remember, every model has to be tested. That means every step in this has to be tested in the lab to basically say the widths of these arrows are the weight factors. Okay, so these are not arbitrary arrows. These things are being measured, and then they end up somewhere, and then they stop at some point, and then people have to make very drastic assumptions to cross. So for example, to produce HCN, if this bridge is not strong enough, I have to make some drastic assumptions to create a situation where this will be valid. And then we found that there are controversies, there are assumptions, and then those assumptions cannot be substantiated and so on. So this is again a very large area of research, and a lot of people are active in this. But we thought of an opposite model. We thought of a model which is top to down, top to bottom model, where because all these Jovian planets and all, they have very low temperatures. So it is possible that they form micro droplets and then they interact with high energy radiation and then they precipitate into complex molecules. Again, this is not a new idea. Such ideas were floated before and people have been trying out in a small scale, but people have been trying out. So we also started getting into this. And recently we did some experiments. Again, I'm going a little fast because there is not much time. But we did these calculations, for example, like here, I'm just quickly showing this is hydrogen cyanide, how at low temperature hydrogen cyanide can form a dimer. And now if such a dimer is irradiated by charged particle radiation or UV radiation, it can actually produce a chemical reaction and a complex molecule can be formed. So this is the hypothesis on which we were working. And we started doing some calculations. And one of our master students, Chinmay, she did this calculations. We built a toy model of our own. Then we improved the toy model by mathematically designing some potentials and so on. And it started giving us very interesting results. But this is work in progress. Parallelly, we took up some activity in the lab where we tried to build a reactor, a Titan reactor. So we wanted to build a plasma reactor which can be used to create Titan-like atmosphere. So this is the reactor. The electrodes are crude electrodes because actually this reactor should not have any electrodes. We wanted to use 13.6 megahertz RF. So we requested our collaborators in IIST to help us. So Safwan and his team, they agreed to help us. But because of this COVID thing, we could not take this reactor to IIST. So in IIST, we could do only with a DC discharge. But with the DC discharge alone, we coupled this reactor to our time of flight mass spectrometer, electron impact. And we did some preliminary experiments. And this is what we observed, that if you take the nitrogen and methane, we took nitrogen and methane mixture into this, which is similar to what you have on Titan, just produce a DC discharge. And we started producing very interesting molecules. So we are now analyzing this information, but I am not in a position to make any scientific comment more than that they are formed, large masses are formed, and we are trying to understand. Hydrogen cyanide is definitely formed. Then C2CN like molecules are also formed, and methyl cyanide and all these things are also formed, and higher masses are also formed, but we are investigating this. So now I want to come to the last 3 slides, the future outlook. So this journey, which started 10 years back where we did instrumentation, did some statistical dissociation, took a flip in last 2 years, 2 or 3 years. We started digging deeper into what this data actually means to humankind. And we started learning that perhaps we need our investigations in the lab to be more focused towards solving the mystery where exactly the life was formed. Because one of the theory, the Vikramasinghe-Hoyle theory, or the theory of panspermia, tells you that the life was actually, or the molecules for life were formed on some comet or something, and then somehow when these things hit Earth, they brought those ingredients to Earth, and then that's how the life started on Earth, because the Earth had the right environment to allow these ingredients to mix and form life. So we still have to solve this mystery. So definitely we need more information about the components of our solar system. We need to do explorations, and we also we need to do experimentations. So we need both. We need the lab experiments and we need space experiments. So where, how, and why? These are the questions which our community can actually help to address. So first, where do we want to go? So there are 2 possible targets. The last one I am keeping as out of question. One is a comet, which will be rich in information, but it will take 20 years because Jupiter is our friend. It protects us from these comets coming to us. But then if you want to meet the comet, you have to go to Jupiter, and that's a long task. Okay. But Ceres, it's a dwarf planet, which is at 3.5 astronomical units from us. And it is possible with our present capability in India to actually reach this place in less than 10 years. So it's a very good target. 40% of the surface filled with carbon, organic carbon, and water is there. It's an interesting target. Jovian planets and their moons, a fantastic target, but it takes minimum 10 years to reach the place. And then you have to have a large enough rocket so that the spacecraft has enough fuel that it can go and stop there or slow down there so that it can get into an orbit and send you the data. Most importantly, it is almost in the present capabilities, it's almost impossible to bring a sample from a Jovian planet. But it is possible to bring a sample from a comet or from Ceres. It is possible. So it would be fun if we can get a piece of this mini planet or a comet and get it in the lab and do the analysis. Towards this, for the comet sample retrieval, actually last year we did an academic project with ISA Supero in Toulouse, where we actually designed a mission. Our students and their students together designed a mission where a spacecraft will go land and pick up a sample, put it into a cryogenically cooled, hermetically sealed capsule and bring it back to Earth. It's really complex. It is much more complex than what I'm trying to make out. So it's not so easy to get a comet sample, but Ceres sample, I'm sure, is something which is definitely possible. How do we do that? The present capability of GSLV Mark III is sufficient to send a spacecraft for in situ mass spectroscopic measurements and other measurements, of course, at Ceres. It's possible. Then what do? We go there, we look for molecular species, chirality, abundance, and radiation effects. Now, why chirality? So several slides before I showed that on one of the comets, we detected glycine, an amino acid. The problem is just the presence of amino acid is not enough. You have to identify whether it is L or D. Its chirality is very important because nature is very selective. Biology is very selective about chirality. So you need a mass spectrometer which will not only detect the mass of the species, it will also detect chirality. So far such a thing is not attempted. Maybe our community can come out with an idea, build one of the first chirality mass spectrometry experiment for space exploration. And I can tell you, at least as far as the organics research in space is concerned, that will be a fantastic step, because life is left-handed. So it will look for left-handed molecules. That is very important. So that is one thing. So this is about the space, what we can do in the lab. This is my second last step before I finish. So we, of course, can build mass spectrometry payloads. We can build aerosol mist and related studies. We can actually do micro droplet studies, actually take nitrogen methane mixture to 95 Kelvin temperature, which is known to be there on Titan, and then irradiate it. They make fine droplets, irradiate it with charged particle radiation, UV radiation, and do measurements. Such a capability already exists in our community. I'm sure if people are interested, they can take it up. Modeling theory, lots of interesting problems are there where we can take up such modeling. Particularly, I'm very keen on doing this kind of radiation pattern in astronomical environments, identify the radiation pattern which these fellows are going to detect or receive, and then try to do corresponding experiments in the lab. That will be very, very useful. So this is another area where we can invite people to contribute. Then the radiation effect, radiation interaction with various molecules, which we are already doing and many other people are doing. But it can be made more focused. Right now, we are just doing, okay, whatever is the simplest, we try to do, like we do naphthalene, we do azulene, because they're the smallest pHs. But I think it needs to be targeted more. And we are also, ourselves, we have now started investigating such targeted molecules. We have to study the formation and stability and spectroscopy of anions, because anions are sort of very choosy creatures. They are very, very delicate creatures. If you find them, the situations are very special, and then it is very easy to zero down onto the conditions compared to anions, because cations, because cations are produced much more easily compared to anions. So this is very important. Then RF and DC plasma reactors for simulating Titan atmosphere, or any cometary atmosphere, or any other, there are many other target molecules. Triton is there, then Enceladus is there, so many different moons, and their atmosphere also can be recreated. on ground, and a lot of information can be gathered from that. And then so on, we can do IR and microwave spectroscopy at low temperatures, identify the molecules positively, and then do the same with either radio telescopes or radio occultation experiments, or actually microwave imaging of the object in space using a satellite, and so on. These are some interesting areas. I think it is very important. The second last point I'm particularly pointing at, it is high time we need a molecular ion storage ring in India, and preferably a cryogenic ion storage ring in India. There is a huge amount of potential in that. And a cryogenic ion storage ring with 2 tunable picosecond laser will be a fantastic facility, and a huge amount of research can be done with that. And I hope someday a group of people will build that. It's not easy. It's not easy. One person cannot do it. One group cannot do it. It requires expertise from many people. And finally, we need to sort of shift a little bit, start taking samples, meteorite samples, and start bringing them to our labs and start doing some sort of mass spectroscopy. So L2MS is another mass spectroscopic technique, which somewhere in India, if we can establish, again, a lot of research can be done. So in a very short span, I have described what motivated us to look into space, what we found in the space, and what now we should look into the space and how. Keeping this in mind, last year, November, we made a small dream plan, sort of a dream plan, a concept note. It was circulated through all the ISRO centers, and we are trying to collect interest from various ISRO organizational bodies, so that somebody, because the propulsion is an interesting problem, lander, sample collection, all these are very interesting problems. Payloads are very interesting. So I hope that we can actually excite many more people to get into the space component of it. But I think that space component will not be very fruitful unless there is a robust ground research happening in atomic and molecular physics research labs. So if we combine these two, I think we as a community should be able to attack. I'm not saying we will solve the problem, but we will be able to attack a problem which is very important for humanity, is that how the life originated. So I believe that if we take a concrete step and use our potential and the potential of our the space research organizations, we should be able to gather more information, make better theories, and who knows, maybe we will be able to identify polypeptides or nucleotides and DNA-like fragments in such environments. And then the identification of origin of life will become perhaps simpler. So I thank my students who have been tirelessly working on this and gave us the capability to reach to this stage. And of course, we will continue these small activities, whatever we are doing at IIST. Preeti, Najib, Vinita, they have just finished their PhDs. They either have done an extensive amount of research as a postdoc. Vinita has just started, and other students have just started their work at IIST. Then we have a lot of collaborators. I have listed a few here. There are others who are slowly joining in. So I hope to have a much bigger list. Here I have projected only those collaborators, those who have supported in the molecular physics work, but we have many more in the other areas which I have not listed here. So again, it's very important that we aim for stars, because सितारों के आगे जहां और भी है, अभी इश्क के इम्तिहान और भी है. So we have to learn much more about our own solar system and atomic and molecular physics, particularly the molecular physics community is at the right place with right expertise to really help in solving this problem. So again, thank you very much for this opportunity. It's more like a dream. I know it's a very metaphorical presentation, but yeah, I think we need to discuss. So I welcome you for any further discussion now or later. Thank you.
Thank you, Umesh, for this very nice overview of things which are happening, outside our atmosphere. And I'm sure there are questions in the audience. So you can just write in the chat box, and then I'll take it up one by one. Arvind, you have?
Yeah. Can I ask?
Yeah, please go ahead.
Hey, nice talk, Umesh. Hey, you were talking about this Tholin dimer, right? Dimer formation, Tholin dimer formation.
Dimer formation leading to Tholin,
Yeah. What kind of calculation is this? Is it a transition state?
No. This is basically just structure calculation.
So you calculate the thermodynamical quantum energy of each state?
No, just binding energy. These are van der Waals clusters. You just calculate their binding energies because you see, because the temperatures there are so low, typically like 90 Kelvin or so, that these potential, the minima in the potential of these clusters is much lower than that. So they actually can survive as dimers or trimers.
Okay. So you check whether it is an exothermic reaction, is that?
Yeah.
Okay.
Actually, there was one graph also. One of the potential energy curve was also there. You could see that there was a nice minimum. And we have many such graphs here.
Okay. You mentioned about this chirality and mass spectra. So what is that you wanted to look at the chirality aspect using time-of-flight mass spectra?
No, because the thing is, when you go to space, you have very limited resources to do investigation of a sample. So typically people will, if they want to do such analysis, they will take a GCMS or something, so that some sample is taken and then it's sort of separated chemically and then injected into a mass spectrometer. And then you have something like an electrospray or something which will then get you the mass spectrum. The problem is it will only detect the mass spectrum.
But do you want to probe any particular aspect of chirality using mass spectra?
No, just identify. Suppose I see glycine.
Oh, okay.
Then I want to know its handedness.
Okay.
Mass spectra will not distinguish it. I need some mechanism there. On Earth, we can do many things. But when you go to space, you have to use the same instrument for multiple things. So it becomes a challenge. So this is
Your voice got stuck.
I think there's some connection issue probably.
Yeah. Okay. Let him come. We lost you in the
between I lost. Yeah. So basically, if somebody builds such an instrument, it will be fantastic. Interesting problem.
Thank you.
Any other question? Okay. So I had a couple of questions. One on the molecular physics aspect, so the experiment that you show, one of the measurements that you were showing, right? I guess it was using this multi-photon absorption.
Yes.
Okay. And now, my understanding would be that even though in lab, one is using multi-photon absorption just to mimic that UV radiation, because you do not have the direct photon with a single energy, right? However, in space, that would not be the case. Of course, multi-photon processes are not supposed to be that relevant. So, do we understand if there is going to be any difference between multi-photon, in terms of reaction dynamics, if the same thing proceeds to multi-photon process or with a single photon process?
That is a very important point, actually. So we do both experiments. We do synchrotron radiation VUV experiments also, extreme UV experiments also. Now, what is important in this experiment, and this scheme is applicable only to those molecules where you can guarantee a certain excited state dynamics. I'll just flash a photograph, okay? So what you're pointing out is actually rather important. You can't generalize it. I cannot generalize it and say, okay, I can always do this. It is applicable. As you said, it is relevant only when this kind of model I can apply, this one. Okay, I can get into the details. Only there we can have this similarity. Otherwise, yes, it is. You can't simply connect the two. They are not equivalent. So that's why those cases where you don't have such situations, you have to go to synchrotron radiations. Only problem with synchrotron radiation sources is like you don't have easy access. Like we get one beam time in a year or one beam time in 6 months, whereas this one is sitting in the lab, so we can do. So the reason why this technique works in PIHS particularly is because of the peculiar excited state dynamics. The lifetimes of these states are so favorable to us that we can make that equivalence, but it is not always. It's a very special case where this is possible.
Okay. Okay, I have another question which is more general, but before that, maybe I'll take other questions. So Vaibhav, go ahead.
Yeah, Umesh, very interesting talk. I had just a couple of questions. One is, what is so unique about Ceres, which we won't see on Mars?
Okay. So Mars is not that organic. If you see the top layer of Mars, which is very well understood, the composition of that, it's mostly inorganic. Whereas Ceres is 40% shown, observed to be that makes it so that makes it rather interesting target compared to Mars.
Umesh, we actually lost, at least I lost you for
half
a minute or so.
Yeah, so basically the main issue is Martian top surface is mainly inorganic. Okay, and liquid water is not there, whereas in Ceres there is liquid water and it's 40% organic. So you will have much more organic chemistry happening there than Mars.
Okay, another question I have is that most of the reactions and most of the models that you talk about, the things are gas phase, right? I mean, all the reactions are in the gas phase with the collisions or association happening in the gas phase. What kind of densities are we looking into? Because don't you think surface reactions are going to be more important than the gas phase reactions in this case?
Very, very important thing. Yes. Yes. So particularly when it goes to problems which are, importance of to interstellar medium, surfaces, clusters, dust particles and dynamics happening on those ices becomes very important. And a huge amount, I didn't talk about it at all, but a huge amount of research is going on. But why we specifically targeted this is because of the aerosols which were detected on comets and on multiple moons, including Titan. So they are not really ices, but you can say condensates, precipitates on which these reactions will happen. But there are some questions which still remain to be answered. For example, I'll just give one example. There is a molecule called quinoline. Okay, it's like its brother of naphthalene, but one of the carbon is replaced with nitrogen. If you look around in the interstellar medium, you don't find it. It's not there. You don't get it. It has very distinct IR bands. You should be able to detect it, but you don't get it. But if you take a meteorite, carbonaceous meteorite, it is rich in this molecule. So then the question you ask is, okay, where did it form? Did it form in the interstellar medium? No, it didn't.
Actually, it is not in the meteorite. It is not as a molecule, but it is higher form of the nuclear-based structure of this molecule is found, right?
No, both. Even pure quinoline also is detected. Quinoline as well as isoquinoline.
Okay.
So these reactions will definitely happen more on the surface, right? As the radiation is processing the surface, as the dust particle is accumulating material and radiation is processing. So definitely surface processes will happen, but we were motivated more towards the upper atmosphere of Titan and some other similar species. So that's why I talked more about gas phase reactions. But yes, finally the dust, ices, they will also, in fact, they will have a major role. But that I did not talk about because that is again, that's a very mature domain and it has gone ahead quite a lot.
Thanks, Umesh. Very nice talk. I enjoyed it.
Thanks a lot.
So we have another question from Shubhadeep. Yeah, please go ahead.
So Umesh, thanks for a wonderful talk. So I have a question about the time scale, what you showed in your initial part of the talk. So you showed that the fragmentation of pH and all this C60, etc., are happening within like, so in this graph, actually, that graph, so it shows like almost 12 orders of magnitude, which is the variant of fragmentation time scales.
Yes.
Like from millisecond to femtosecond. So
Yes.
I'm pretty sure that after the energy deposition by like photon or charged particle, so this is just not a single process which is governing the fragmentation pattern. So femtosecond or less than femtosecond, I still understand maybe electronics degrees of freedom or some sort of phonon degrees of freedom is playing a role. But I'm more curious about like how it happens, means above picosecond timescales. Means I cannot think a mechanism.
If I have to consider a statistical dissociation process, picosecond itself is an overkill.
Exactly.
We talk about it below that time scale, not above that time scale.
So how are you getting that picosecond to millisecond time scale?
No, that we don't get right now. Here, if you see, the time scale goes only up to something like 100 nanoseconds or so.
Okay.
Actually, if we have a supersonic jet, we can bring it down to something like a few nanoseconds, because the laser pulse itself is 5 nanoseconds. So we can bring it down to that. I didn't show the simulation, but in the simulation, we include the thermal spread. So basically what you see here, the main reason of this spread is thermal. If I shrink that, right now my sensitivity here is of the order of 100 nanoseconds. We can bring it down by an order of magnitude. That's possible. And if you use a picosecond laser, it can be brought down further, but again, it cannot go below, like say, nanosecond or so. Below that, it's not possible experimentally, at least kind of instruments. You need a proper pump probe experiment or something that will not work.
But intrinsically within molecules, some dynamics is happening in like picosecond or more time scale, right?
Yeah.
So there I'm more curious, means how can it be?
So, so this one, for example,
isn't it you do for large molecule like pH? Sorry to come in. When you have a large molecule, the statistical redistribution of the energy, excitation energy, with the large number of modes available, you could expect very well microsecond lifetimes, right?
Okay. So essentially, it's going to statistically going to other degrees of freedom.
It's an IVR process.
Yeah, but before that, you have to have this process. So you can see this particular one for azulene is experimentally measured to 120 femtoseconds. But that is internal conversion. It's not thermalization. Thermalization will take picoseconds because so many degrees of freedom are there, and you have to really distribute this energy. So, but the precursor to that will be IC or whatever similar process. So you have to, so pump probe measurements will do this for you using a femtosecond laser, but the thermalization will take much longer time.
Okay.
The thermalization, and if I'm wrong, correct me, thermalization, and then finally a particular mode has to gain energy, activation energy for fragmentation. So that takes this lifetime, right? Microsecond.
Yeah. So that will be like how much energy is available in the reservoir and how many degrees of freedom you are left with. So.
Okay. Thanks.
Okay. So I don't see any other question. So let me just satisfy my curiosity, right? And then we can probably end this talk. See, what it seems like is that we are looking for signatures of life or organics, right, in the outer space. And in that we are coming up with two scenarios. One is we are looking for them in comets, which are coming from far away in our solar system. We are looking for them beyond the Jupiter's orbit, right, in the Jovian moons, and then beyond that. Or we have, of course, abundance of organics on Earth, right? But near Earth, somehow we have all this sterile environment. The moon doesn't seem to have anything interesting going on. The Mars is not, the Mars's moon does not, right? Inner planets are definitely not going to sustain anything. So what could be the reason for this? or do we like have understanding of this?
No, I have no idea. But what I understand is that and this is very, this information purely comes from some review articles and not from an expert view. Is that the way the solar system was formed, the protoplanetary disk, these places were more rocky. Earth, Mars, Venus, they were more rocky, more inorganic. Whereas the methane, nitrogen and all, they were more on the outskirts. So you will see that, for example, even Jupiter and all, they're filled with organic molecules. You can detect benzene from Earth on Jupiter. It's that much in quantity. So yeah, I mean, I think that is the reason, but how that happened, I cannot tell. But apparently the mass distribution and elemental distribution in our protoplanetary disk decided this. That alone, I do not know how it came.
Okay. So, yeah, Bhargav, yes, please go ahead.
Hi, Umesh.
Hi.
Nice talk.
Thanks.
Quick question is the molecules that you mentioned, detection of these chiral molecules in space. So was it that their mass was only detected without knowing chirality, or it was also inferred that they were left or right handed?
We don't know that. Right now, what we know is their only masses are known. Their handedness is still not known. Where did it go? Molecular zoo. Sorry,
Okay.
I'm just searching for that. Yeah.
So
Detected
would it
only
also
as
help? Would it also help to kind of decipher if you detect other masses in the same mass spectrum and try and see what are the possible channels?
Yes, but that would help if you are doing electron impact, I think. I think these ones were done using a GCMS experiment.
So essentially it is a lab-based thing.
Yeah, so the fragmentation will be a little less. No, this was actually one of the payloads on the spacecraft.
Payloads, okay. So the payload had a GCMS.
Yes.
Okay.
But then
but you
it won't fragment too much in that. It's very gentle.
Okay. Yeah.
But yes, electron impact should be able to tell us, or something like an MSMS, if we do MSMS or something like that. Yes.
No, electron fragmentation will tell you the handedness.
I don't know.
Okay.
We have already studied them in some detail where some signature is there in the fragmentation spectra, perhaps. I don't know.
Okay. Thank you.
Thanks. Okay.
So I think if there are no more questions, then let me thank Umesh on behalf of the society for accepting our invitation and giving this exciting talk, slightly off the normal atomic molecular physics talks that we hear. Right? So thanks a lot. And thank you all for joining us today. We'll have next colloquium scheduled in the couple of weeks, and I'll send the information in due time and hope you guys can join in there. Thank you.